Welcome 1100. Today we're going to analyze ring pendulums. Now that is one of these, and what I'm going to do is my best not to talk about any of the theory behind what we're going to do today. You're given a formula. Period is equal to 2 pi divided by the square root of g times the square root of d, where d is the diameter of this ring. There's a lot of subtleties involved with that expression, and I would love to talk about them, but I'm just going to commit to myself right now not to. Okay. I'm just going to pass along to you the necessities, what is necessary to complete this lab. Now, for D, the diameter, I don't think your lab manual makes reference to the inner or outer. Well, actually, it does make reference to the outer diameter. We're supposed to use these things again for the larger rings to determine the diameter of the larger rings. What I want to bring to your attention is that technically what you should be doing is measuring the diameter at the midpoints. So not the outer, not the inner, but well, the average of the two that would place you right in the middle to middle. So what I'll do is I will help you measure these, and I'll do that by, well, what we've typically been doing. For the smaller rings, we have 3 small rings that fit in the jaws of a vernier caliper, and I don't have a caliper on hand, but you'll get a photograph with this in the jaws of that vernier caliper. Then you will get a photograph of the caliper focusing on the 0 tick mark on the sliding scale. And that will enable you to determine the 1s and the 10th place of the measurement. Then I will give you another photo of that same caliper in its same position, but I'll focus in on the sliding scale, and that will allow you to accurately determine the hundredths and thousandths place of the measurement. So for each of the small 3 rings, that'll be 3 photographs, right? Also, I will clamp the caliper around here so that you can measure its thickness. And you'll use that measurement to determine the diameter of interest. Well, all it is just outer minus the thickness, right? So you'll have like 3 photographs for that measurement as well. Then when we get to the larger 3 pendulums, here's the largest one here. I'll use the caliper I just placed on the ground and clamp that around here. You'll get a photo of that. Then I will place a ruler, a meter stick across here, and I'll take 2 pictures, one on the left side, one on the right side. You know the drill. So you can get accurate measurements. So you're going to have a lot of photographs that accompany this video, and you will use those photographs to determine all of our diameters. Now, when you are in the lab, what you would do is, well, there would be a post on your lab bench, and then there's this little metal blade sticking out, which this is seated on, and you get it swinging back and forth. So, you know, you have a stopwatch and you time X number of periods. In fact, your lab manual suggests that you get this swinging for at least 20 seconds, or up to 20 seconds. They phrased it in a weird way. I think they said up to 20, well, anyway, 20 seconds. And why do we do that as opposed to just measuring 1 period, right? All we're after is just the time of 1 period. The biggest error introduced in this experiment is due from our reaction time. So start and stopping the clock is going to be whatever our reaction time error is times 2. So if you have a small period like we are going to have for these smaller rings, the reaction time error is going to be like 50% of our actual measurement, 50% of the period, you know, or can be. So that's why they want you to measure a large number of periods. Now, we don't need to measure that many periods. And the reason being is that we're going to do this in a more of a controlled fashion. In fact, doing this experiment online, believe it or not, is going to give us way better results than if you were doing it in person. And the reason being is, actually, I'm sorry, hold on a second. The reason being is that I'm going to film it in slow motion. This is the blade I was talking about. Normally in the lab, you wouldn't have this. So we have this backdrop, and I marked this center line is our equilibrium position, or 0 degrees. First line is 8 degrees, next is 9, and the last is 10 degrees. So when this thing is swinging in slow motion, it is going to be a lot easier to start and stop the clock at the appropriate times, as opposed to this swinging back and forth in the lab in real time. Furthermore, you're going to notice in the video that there's a little black mark on the bottom of the ring. So I get this in motion, and you could wait. This will be oscillating back and forth. You can wait till the amplitude it pertains to, say, 10 degrees or 9 or 8, one of those lines. I say wait because as it's swinging back and forth, of course, it's going to be losing energy due to frictional forces. So over time, the amplitude is going to get smaller and smaller and smaller. So right when the amplitude or displacement turns out to be at say 10 degrees, that's when you could start your clock, and time, say 5 periods. For me personally, I viewed the video already, it's already been done, and I found that 5 periods works well for the first, was it for the first 3 or 4? The first 3 or 4 pendulums, and then the last 2 or 3, I forget. All that was needed was 4 periods. Let's see. Oh, timing it. How do you time something if it's in slow motion, right? What I did was I just simply put a stopwatch in view of the camera. So while this is moving in slow motion, you'll see a stopwatch that is in slow motion as well, but it's going so slow that you could determine the times of interest. Actually, it may be better if you did it with a partner. What I did was I would pause the video and then look at the clock, just to be like really accurate. But the thing is whenever I pause it, my black mark here would be off a little bit. I would notice that it isn't at its amplitude, it's almost there, or I press pause too late and it's slightly on its way down. So I would just rewind the video again and start it again and hit pause and wait for it to be right on that mark. But if you had a partner, I guess it'd be a lot easier. One person could just look at this while the other person looks at the clock. The person watching the ring could say, okay, now, or whatever. And the other person would record the time, however you want to do it. I'm just, let's see. I'm giving you a heads up of what you're going to see and what you'll need to know to do this experiment. That is about it. Oh, one other thing. One of these rings actually was welded kind of wrong, and it's a little beat up. It was extremely difficult to get it in motion. Well, not get it in motion, but get it in motion in the correct way. This needs to be oscillating in a plane that is perpendicular to the blade. right? And so it's not that easy, especially for that deformed one. It was like kind of like wiggling all around, but I finally got it. It took a while, but we're all good with how they are oscillating. And I bring that up because as it turns out, I have fluorescent lights in here that act as strobe lights. I mean, they're doing it right now. I was totally unaware of it until I watched this video in slow motion. So since they're plugged into a voltage that's going at 60 hertz, I guess they're flashing 60 times a second. And it's annoying when you're watching the video. My solution to that was gonna be to just get a work light that doesn't have fluorescent bulbs, right? They have halogen bulbs, and so that wouldn't blink, so then we wouldn't get that effect. But that would entail me doing this all over again with 6 different rings, one of them which was deformed and took me forever to get swinging right. So you could deal with the little flashing lights, right? So I'm not going to do it again. The only question I have in my mind right now is whether or not for each ring to give you a segment of video where it's swinging back and forth like 20 times or whatever, and you just pick out which periods you want to use, when to start the clock, when to stop the clock. Or I'm thinking maybe I should condense it, but then that would make it too easy for you. If I condensed it to only 5 periods, then there wouldn't be any discretion on your part on how to time it. Well, that's still up in the air. I'll hit the editing room in a second and I'll make that decision then. But anyway, let's see, we got the diameter. I think that is about it. There's 2 things you want to compare, and for one of those, I'm just calling them things so that I'm not giving too much away. One of those items was like 0.5% air, and then the other one was a larger air, only 1% though. So if you measure this right, you are going to find that you'll be pleased with the results. So let's get started. All right, and that's enough talking for me. So I'll see you next week.